In the last lecture, we were examining unsteady unidirectional transport in an infinite medium in a Cartesian coordinate system. So, the configuration was a surface at z is equal to 0, which is a boundary for an infinite fluid in the half space z greater than 0. The fluid and the surface are initially at the same temperature T infinity, that is they are both at the same temperature, and at time t is equal to 0 the temperature of the surface was increased instantaneously to T0. And we were trying to determine what was the temperature profile within the entire system and what is the flux at the surface. Though this seems a rather idealized configuration, it is valid for real systems, for example, where even if you have a finite height of in this case the length scale L as shown here, okay, provided that height is much larger than the penetration depth of the temperature profile at early times, you can use this solution, and we will see later how that solution is used for finite systems. We had scaled the temperature T star so that it is equal to 1 at the surface and 0 far away. Once you scale it in terms of T star, then the same solution applies regardless of what is the actual value of T0 and T infinity, because you can always reduce these to T star and then solve the equation for that. So, we had scaled the temperature. There was no scaling for the distance because this is an infinite medium. Okay. And just based upon dimensional analysis, the only parameters here are z, the distance from the surface, alpha, the diffusivity, and t, which is time, and you can create only one dimensionless group from this, okay, z by square root of alpha t, which we had designated a similarity variable psi, and we had expressed the temperature equation in terms of the similarity variable psi using chain rule for differentiation. Using chain rule for differentiation, the first and second derivatives with respect to time and with position, using chain rule for differentiation, and based upon that we had got a similarity equation. Okay, we had got a similarity equation which is shown here. Okay, so the similarity equation, which is does not depend independently on z and t, but depends only through its dependence on the similarity variable psi. In addition, we were able to express the boundary conditions also in terms of psi, and based upon this I had got a solution for you. Okay. I had got a solution for you. The temperature is equal to 1 minus this error function of psi by 2. Okay. Where psi is z by 2 root of alpha t. Okay. So, that was the final solution, and we had also got a solution for the flux. Okay. And I had gone through the a simple example to demonstrate how this can be used for a finite system. Okay. If we have a finite system, but the height of the system is much larger than the penetration depth. The penetration depth just from dimensional analysis is square root of alpha t. Okay. It is comparable to square root of alpha t just from dimensional analysis. So, the height of the system is much larger than square root of alpha t, then you can use the solution that we have. Now, the solution was expressed in terms of the error function. Okay. The solution was expressed in terms of the error function, and these special functions may seem intimidating at first, but they are just functions like, for example, exponential functions, sine functions, cosine functions, and so on. Okay. So, I will just go through a little bit on what this error function is, so that you can get a little familiar with that. Okay. Okay. The error function is formally defined as error function of x is equal to 2 by root pi integral 0 to x dx prime e power minus x prime square, okay, where x prime is the variable of integration, the dummy variable. Okay. And the dependence of the right side on x appears only through this dependence of the right side on x appears only through this upper limit of integration. Okay. So, as I said, the error function is 0 at 0 because you are integrating between 0 and 0. So, there is no area under the curve. Okay. As x increases, the error function of x increases, okay, until in the limit of large x this error function becomes 1. Okay. In the limit of large x this error function tends to 1, it is 0 at 0. Okay. Okay. The slope of this error function, okay, d error function of x by dx. Okay, the slope of this error function, the slope of an integral is just the value of the integrand at the upper limit. Okay. The derivative of an integral is the value of the integrand, okay, at the upper limit. Okay. The value of the integrand is 2 by root pi e power minus x square. Okay. That is the slope at x is at a value of x, and you can see the slope is e power minus x square. So, it decreases to 0 as x goes to infinity. At x is equal to 0, the slope of this error function is 2 by root pi. Okay, that is the slope of the error function at x is equal to 0. So, this is the formal definition of the error function. The error function is also a solution of the equation, the differential equation d square f by dx square is equal to minus 2x df by dx. Okay. The solution of this equation is the error function. Second order differential equation, one solution is the error function. The other solution, as you can easily verify, is if f is a constant. Okay. If f is a constant, the right and the left sides are both equal to 0, and therefore, f is equal to a constant is also a solution of this equation. The error function is the second solution. Okay. You can solve this by the substitution w is equal to df by dx, okay, which imply that dw by dx is equal to minus 2x w. Divide throughout by w, multiply by dx and integrate, and you will get log of w is equal to minus x square plus some constant, or w is equal to c e power minus x square, okay, which is df by dx. Okay. Okay, a simple manipulation, write df by dx as w, then it becomes a first order differential equation for w. That differential equation, divide by w, multiply by dx, integrate both sides, and you get w is equal to c e power minus x square, which is df by dx, which means that f is equal to c integral 0 to x dx prime e power minus x prime square. Okay. So, that is the function, that is the error function, in which the constant c is chosen such that the error function goes to 1 as c goes to infinity. Okay. So, this is the constant is chosen so that the error function becomes 1 as x goes to infinity. So, that is the equation for the error function. Okay. If you recall, the equation that we had was d square t by d psi square is equal to minus psi by 2 dt by d psi. Okay. So, there was a difference in the constant, okay, between the equation for the error function and the equation for psi that we had. So, we can get a general solution for the equation of the kind. Okay. If I have an equation of the kind d square f by dx square is equal to minus a x df by dx. Okay. I can transform the variable x is equal to x star is equal to x root of a by 2. Okay. which implies that d by dx is equal to okay. Okay, so df by dx, okay, which is root of a by 2 df by dx star. Okay, just using chain rule for differentiation. And if you substitute that in here, right, what you will get is that a by 2 d square f by dx star square is equal to minus a x star df by dx star. Okay. On the right side I have x times d by dx, and therefore the constants will cancel out. Okay. The multiplicative constants will cancel out, okay, and I can cancel out a on both sides, and I will reduce this equation to the same form as this one. Okay. This equation will be reduced to the same form as this one, and this implies that the solution for this is f is equal to error function of x star. Okay. One of the solutions, the other one is a constant. Okay. It is okay. It's equal to a constant times error function of x star times error function of x star is equal to a constant times error function of x root of a by 2. Okay. In this equation, the equation that we were solving for, a is equal to a half. Okay. A is equal to a half in the equation that we were solving for. Therefore, square root of a by 2 is going to be equal to 1 by 2. Okay. And that is the reason that we had got the solution t star is equal to some constant error function of x by 2. Okay. So, that is the simple transformation. Okay. So, this is how you can use standard equations in order to determine the solution of an equation. So, this error function which is defined formally in this way, okay, which is defined formally in this way. Okay. You can the differential equation for the error function is given by this one, and by a simple transformation of coordinates, okay, by a simple transformation of coordinates, I can get the solution for any coefficient on the right side, which is what I had done when I calculated the error function, okay, the solution for the temperature field. Okay. So, on this basis, and after applying the boundary conditions, I got t star is equal to 1 minus error function of x by 2. Okay. So, that is a brief summary of the error function and its use for getting a solution. Of course, if you have to do numerical calculations, you have to evaluate it from some tables or by some numerical method, which is what we had done in this case. Okay. When we went from this step to this step, okay, when we went from this step to this step, okay, I had inverted the error function. I had a solution, error function of psi by 2 is equal to 0.525, invert that to get psi by 2 is equal to 0.5 from for example, a graph of this kind, okay, from for example, a graph of this kind, okay, so or from standard tables. Okay. So, that is how you do it, evaluate these functions numerically. So, that is the solution that we had obtained using similarity transforms for this diffusion into an infinite domain for heat transfer. Okay. The same solution actually applies, okay, for mass or momentum transfer. Okay. The problem that we had actually solved. Okay. T is equal to T naught, T equals T infinity, okay, and at z is equal to 0, t at initial condition. For all z in the fluid, that is for z greater than 0. Okay, that was the problem that we had solved, and we had got this temperature profile. Okay. The T star is equal to T minus T infinity by T naught minus T infinity, 1 minus error function of z by 2 root alpha t. Okay. The same thing I can do for a mass diffusion problem. Okay, the same thing I can do for a mass diffusion problem. In this case, I will have c is equal to c naught here. This is the z coordinate. Okay. C is equal to c infinity far away, and at t is equal to 0, c is equal to c infinity for z greater than 0. The equations are the same, only you have to substitute concentration for temperature and mass diffusivity for thermal diffusivity. Therefore, the solution is also going to be the same. Okay. C star is equal to c minus c infinity by c naught minus c infinity, 1 minus error function of z by 2 root of dt. Okay. Substitute mass diffusivity for thermal diffusivity and concentration for temperature. Okay. The same thing can be done for a momentum transfer problem. Okay. The same thing can be done for a momentum transfer problem. Okay. In this case, I will have a surface at z is equal to 0. Okay. And far away from the fluid, Vx. Okay. So, I will take a coordinate system here. Z is the distance from the surface, x is the distance along the surface. Vx is the direction of flow, the transfer of x momentum. So, Vx is the direction of the momentum, and z is the direction of momentum diffusion. Okay. Z is the direction of momentum diffusion, and x is the direction of the momentum. Okay. So, I will have Vx is equal to 0 far away. So, you have a stationary liquid far away or a stationary fluid, and at time t is equal to 0, this surface has a velocity Vx naught. Okay. And at t is equal to 0, Vx is equal to 0 for all z greater than 0. Okay. So, the physical configuration is you have a surface, a flat surface, initially stationary, and at time t is equal to 0, instantaneously you move the surface with a velocity Vx naught. Okay. And then you want to find out what is the velocity profile in the x direction as a function of position and time. Okay. As a function of z and t, you want to find out what is the velocity profile in the fluid, because you have started this bottom surface moving with a finite velocity. Okay. So, this is the transfer of x momentum in the z direction. Okay. And the solution for this will also be of the form Vx star is equal to Vx by Vx naught. Okay. In this particular case, we had the velocity far away is 0. So, Vx at infinity is equal to 0. So, I have only Vx by Vx naught as the scaled velocity. This will be equal to 1 minus error function of z by 2 root of nu t. Okay. Substitute the momentum diffusion coefficient for the thermal diffusion coefficient and the velocity for the temperature, and the equations are the same. Okay. The momentum conservation equation is obtained by substituting velocity for temperature in the energy conservation equation and substituting kinematic viscosity for the or momentum diffusivity for the thermal diffusivity in the energy balance equation. So, the solution is also the same. And if you recall, we had got the solution for the flux qz, okay, at z is equal to 0 is equal to k into t naught minus t infinity, okay, by root of pi alpha t. Okay, that was the flux at the surface. That flux decreased with time as t power minus half. Okay. You can get the expression for the mass flux in a similar manner. Okay. Jz is equal to k into c naught minus c infinity by root of pi dt. Okay. You will get exactly the same relation. And for momentum transfer, tau xz is equal to mu, okay, into Vx naught. Okay. Vx infinity is 0 in this case by root of pi nu t. Okay. In this case, the stress is the negative of the momentum flux upwards, because it is the force exerted on a volume whose outward unit normal is in the z direction, and therefore, the momentum increases for the surface below, and this will have a negative sign for that reason. Okay. Okay, so, the same solution can be used for energy, mass and momentum transfer, because the equations are the same, only the variables change: concentration, temperature, velocity. The diffusion coefficients change: thermal diffusivity, mass diffusivity and momentum diffusivity. So, the solutions are all the same. Okay. So, by solving this one problem, I can get a solution for by solving one problem for thermal diffusion, I can get solutions for mass diffusion and momentum diffusion as well. Okay. So, let us go on to apply this for a problem which is at steady state, but which is not temporally evolving. Okay. So, I will just set up the problem for you. I have a vertical surface down which there is a film of liquid that is flowing. Okay. Okay. Down which there is a film of liquid that is flowing, and I will call this as the z direction into the film, and this is the x direction going downward. Okay. And there is a gas which is going upwards, okay, which contains a pollutant, and this pollutant is being absorbed into the liquid, it is being dissolved into the liquid. For example, in a stripping process where you want to remove certain constituents from the gas for environmental regulations. Okay. So, this gas is being this gas species is diffusing into the liquid. Okay. We will assume that the rate limiting step, the slowest step, is the diffusion into the liquid, and assume that the gas concentration is homogeneous. Okay. The gas has the same concentration everywhere, and the rate limiting step is the diffusion into the liquid. When the gas dissolves in the liquid, the concentration at the surface is the saturation concentration Cs. Okay. And at the other side, we have a solid surface, so there is no penetration within into the surface. Okay. So, the flux, okay, Jz has to be equal to 0 at the surface. And the fluid film is flowing down with a velocity profile that we had already calculated, a parabolic velocity profile. Okay. It is flowing down with a velocity profile which is a parabolic velocity profile, which we had already calculated, okay, for the flow down an inclined plane. The same solution will apply in this case if I set the angle of inclination theta is equal to 90 degrees centigrade. Okay. So, here what we have, okay, this is a spatially varying problem. There is a variation in concentration with respect to both x and z. Okay. So, we cannot straight away use a solution for a temporally varying problem. Okay. However, we can make one transformation. Okay. That is that a parcel of fluid that is moving downwards, okay, okay, a parcel of fluid that is moving downwards, okay, at the interface. Okay. I just expand that out, and this is moving with a velocity which is nearly a constant. Okay. It is moving with a velocity which is given by this velocity. So, this is a parabolic profile. At the interface, the slope is equal to 0. So, near the interface I can assume that the slope is a constant. So that near the interface I can assume, because the slope is 0, the velocity can be approximated as a constant. Okay. That constant value is the maximum velocity. Okay. So, as this parcel is moving along, right, if we neglect the diffusion in the x direction in comparison to the cross stream diffusion, and if the penetration depth is small compared to the thickness of the film, I will call the thickness of the film as h, say. If the extent to which the solute has penetrated into this film is small compared to the thickness h, right, then I can consider this as a parcel of fluid, okay, which has been exposed to the gas at the interface for a finite time. That finite time is the residence time of that parcel of fluid within the falling film. Okay. So, the exposure to the gas starts at z is equal to 0, okay, the exposure to the solute starts at z is equal to 0, and as it progresses downwards, okay, it gets exposed to the gas for a finite time. Okay. The time of exposure okay, is going to be equal to x by V max. The distance travelled by the velocity is the time of exposure. Okay. And since I have assumed that the thickness of this film is small compared to the total thickness, I am assuming that the penetration depth of the gas into the film is much smaller than the film thickness. This is equivalent to diffusion into an infinite medium. Okay. This is equivalent to diffusion into an infinite medium for a time which is given by this exposure time. Okay. If the thickness of the penetration depth of the solute into the film is much smaller than the thickness of the film, then the film effectively appears to be an infinite medium. Okay. The film effectively appears to be an infinite medium, and therefore, this is similar to the flux the flux this is effectively equivalent to the diffusion into an infinite film for a finite time t, which is given by the exposure time. So, at a given location x downstream from the start of the contacting section, at a given location x downstream from the start of the contacting section, this parcel of fluid has been in contact with the gas for a time t, which is x by V max. Therefore, this is equivalent to the concentration profile you would have had for a system that is diffusion into an infinite film whose exposure time is given by x by V max. Okay. And that solution is C is equal to C s into 1 minus error function of z by root dt. Okay. The concentration profile for a film of for the diffusion into an infinite medium, okay, after a time t is given by this, okay, Cs into 1 minus error function of z by root dt with boundary condition C is equal to Cs at z is equal to 0. Z now is this coordinate, okay, z now is the distance from the film, okay, C is equal to Cs at z is equal to 0 and C is equal to 0 as z goes to infinity. Okay. For this boundary conditions and the equation partial C by partial t is equal to d partial square C by partial z square, this was the similarity solution we had derived. Okay. For this spatially varying problem, all I need to do is substitute t is equal to this exposure time, okay, and I will get the solution. Okay. So, therefore, the solution for the spatially varying problem is equal to C is equal to Cs 1 minus error function of z by, I made a mistake here, it should be 2 dt, okay, 2 root dt. So, I will get z by 2 root of d x by V max. Okay. So, this is the solution I would get, okay, for an exposure time x by V max. I will continue this in the next lecture and explain it a little bit more, how I can transform a solution for a time dependent problem to a solution for a spatially dependent problem, and we will look at an example of that as well. I will continue this in the next lecture.